Let's show now the following theorem, that if P is a limit point of a set E, then every neighborhood of P contains infinitely many points of E. So what are we saying? What are we saying here? It's easy to understand if we have a sequence in R, right, that is converging towards a limit. It can go from both sides, right? But the idea we have of convergence is that whenever no matter how close I look to the limit point, I will always see infinitely many terms of the sequence, okay? The closer I get, I keep seeing infinitely many points, infinitely many terms of the sequence, okay? So that is the idea we need to have in mind, the idea of limit point. But anyway, what does this mean in higher dimensions? Sorry. Let's give a definition to what the limit point is. So a point P in E, okay, is a limit point. We say a limit point of E, okay, if every neighborhood well, let's not give it a name, every neighborhood of P, let's keep it like that, contains a point Q in E that is not P, okay? So that means no matter how close we get to P, okay, that point P in E, we get smaller and smaller neighborhoods around it. We will always find at least one point of E that is inside that neighborhood. We say one, at least one, but actually we will have infinitely many points that are inside the neighborhood, okay? So let's get to the proof of the theorem. So here we are going to do by contradiction, right? It says every neighborhood of P contains infinitely many points of E. Let's assume not. Assume by contradiction, okay, that there is a neighborhood let's say N of P, okay, which contains only a finite number of points in E. Okay, so what we are saying here, we have this neighborhood N, point P, and we have just a few points that we are going to call Q1, Q2, Q3, Q4, Q5. Okay, like that should be enough. Let's say these Q1 through Qn are those points. Of the intersection of N with E, okay, which are different from P. And now here comes the trick. What we can do is to consider a new radius, okay, which is the minimum of the distances, we're using D, the distances from P to each of these Qn, okay? Let's call it M, Qm. So I'm going to be checking all the distances to all these points. And then taking a radius that is smaller than the smallest of these radiuses, okay? And once I do that, then I'm able to take a new neighborhood of radius r, okay? And then this neighborhood does not contain any point Q of E, okay? Other than P. Okay, so that means that this goes against the definition of P as a limit point. And we have a contradiction. Okay, so we are done. Here there is a subtlety that someone could argue. Say, wait a minute, can this minimum be 0? But actually, if it's a minimum of a finite number of quantities, that cannot be 0, okay? Because we are choosing among a finite quantity, a finite number of choices. But if we have infinitely many points, okay, the infimum, it could be 0, okay? So this is important. The minimum is different from an infimum, okay? When we have a minimum, it's better because that means we have a finite number of choices, and that makes usually proofs a little easier,